So now we get to start using exponentials and logs in real life context. And this is actually a section that has the most real world context of the entire course. So there are science applications, there are financial applications, business, so many applications. So that it really makes this one of my favorite sections of the whole course. And that we have 6.8 is exponential growth and decay models, and that's really mostly science-based. And then 6.7 is financial models, and so there's the business aspect of things in this course. So we get to apply the things that we've been practicing, and it will make you stronger at solving exponents and logs too as you do these problems. All right, so first of all, a little formula for uninhibited exponential growth and decay. So uninhibited exponential growth and decay, that truly means it is going to be a science application. And there are so many different things in science that we're going to look at for this. So our model is going to be A of t is equal to A naught times e raised to the kt. All right, so the reason we're using these specific letters, okay, is because A of t stands for the amount at time t. Okay, so A and t, because it's amount and time, it's not f of x, although this is a function, it is function notation. And then A naught is A with a little sub-zero, and that is the initial or original amount. That's a common they call it naught. It's like NaUGHT. That's a common science term. You may have heard it in some other classes. The original amount, and of course, since it's the original amount, it is actually at time t equals 0, okay? Because that would be when it started. So when t is equal to 0, this entire term is 1, and A naught is the amount at time t equals 0. All right, K is a constant. So that's going to be your growth or decay factor or constant. If K is greater than 0, you are going to have growth. And if K is a negative number, less than 0, you're going to have decay. So let's look just at a first initial problem that will help us to start understanding this concept. So a colony of bacteria that grows according to the law of uninhibited growth is modeled by the function n of t equals 100 e to the 0.045, n is measured in grams and t is measured in days. So when we answer these questions, we are going to use units when we can. It says determine the initial amount of bacteria. So we can use our equation, right, to say, well, actually A naught is right here. The initial amount is 100. Oh, and I think we're missing somehow on this paper, the T didn't come through. I think on yours it probably does say T right there, but it wouldn't make sense if there wasn't a T. So it's N of T is 100 e to the 0.045 T. The T is up there in the exponent as well. Maybe it just got so tiny it fell off the page. I don't know. All right, so the initial amount of bacteria is 100. It's not 100 bacteria. That's ridiculous. It'd be millions, right? It would be 100 grams of bacteria. I don't think they can count individual bacteria like that. I don't know. What is the growth rate of the bacteria? Okay, well, that's asking for the K value. So the first one we were asking really for the A naught value. For the K value, looking in the equation, it is 0.045 0.045. And that's why we know it's a growth, because it is a positive number. Okay, next, C, it says graph the function on your calculator. So we're going to look at that because I can't say for sure that when you graph it, you'll know exactly what to do. So go into y equals and type in your equation, 100e to the 0 point, or the just 0.045x. There is no t, like when you type, that's the variable, so that's the variable x right there. Then hit graph, and if you're like me, that's probably what you'll see, a whole lot of nothing. And that's because, I mean, you may notice that the initial amount was 100, and it probably goes up from there. So we're going to need to change our window. So let's change our window. Now the X, remember, that was where we wanted a T. So that's the time. Okay, so if you look at our problems, it's going to ask about 5 days. And so we need at least X. We don't really need negative. So we could really go to we could keep it at -10, or we could put x is equal to 0. That's fine too. I think maybe I'll just change that to 0 because I don't want to go back in time. Okay, now the x max I could keep at 10, or I could go a little bigger. We'll just leave it for 10 days for now. Okay, now the y is where we need to change. I personally like to keep the bottom there, so keep the -10 so I can see the x-axis. But I probably want my y max to be over 100, because 100 is where we started. And so I'm going to make it, let's see, it says, does it ask? It asks for when will the population reach 140 grams? And it also asks what is the doubling time. So doubling would be 200. So let's just put in like maybe 220. That would be 220 grams. Okay. So it's really essential to include the window. Okay, so it is going up. It doesn't look as exponential as I thought it would, but I think that's because of the scale, right? So if we draw that for part C on our paper, it looks something like that, right? And we know that this value is 100 right here. We know that this is the time, and this is the amount at time t. Okay. Now, that was part C. What is the population after 5 days? Okay. It really helps if you label your axes, because then you could say, well, here's 1 day, 2 days, 3 days, 4 days, 5 days, right? So we know that we want to put in the x value of 5, or the t value. So we can, for part D, we are looking for the a of 5. Okay, so we have 2 ways we can do this. We can just type in 100e to the 0.045 times 5. Okay, that's going to give us the amount after 5 days. Since we already have this graphed in our calculator, I want to show you a cool way to quickly do this. So when you're on the graph, if you go to second and then calculate, so it's behind trace right there in red, the first thing you see is value. So we want to do number 1 value, and we just want to put in x equals 5. Okay, there it is on our graph, x equals 5 and y equals 125.232. So 125.232, remember that's the amount in grams. All right, part E. How long will it take for the population to reach 140 grams? Okay, so is it 5 days? Less than 5 days? More than 5 days? More than 5 days, right? Because right at 5 days, we have 125 grams. We need to keep growing until we get 140 grams. So equation-wise, it looks like this. 140 is the amount at time t, equals to 100 e to the 0.045 t. Okay, so use the equation, but this time what we know is the amount. Let me just erase this little dot. I don't need that. Dot, you're in the way. Uh-oh, it doesn't want to erase. Ah, there it is. Okay, so we need the amount, and then we're looking, or we know the amount, and we're looking for the time. So we can solve this using logs, yay! Or we can actually solve this in our calculator. So let's look at the way to solve using logs first, and then look at the calculator. So first we would divide both sides by 100. Okay, so 140 over 100, I'm just going to change that to 14 over 10. I know I could reduce it further, but that's fine. And then e to the 0.045 t. So now we're going to change this to log form. So log, since the base is e, is natural log of 14 over 10 is equal to 0.045 t, right? To solve for t, just divide both sides by 0.045. And then type that into your calculator. So let's see. Quit. Okay, so we need the natural log of 14 over 10. And then we're going to hit enter and then divide by 0.045. 7.477. So t equals 7. Did I just seriously forget that again? Hold on. 477. I knew I was going to say the wrong thing, so I'm glad I checked. 477, and then remember, this is the time in days. Okay, that totally makes sense because we knew it was going to be longer than 5 days to get to that 140. Just real quick, I know this video is getting a little long. Sorry, it's a long problem, lots of parts. But if we were in our graph, we actually could find this as well. So we are looking for 140. We would go back to y equals, and in the second y, we would type in 140. And then hit graph, and what we'll see is a horizontal line. So really, on our own graph, what we're saying is here, when is the amount 140? And we're making this line, and where this intersects here, that is our answer. So let's see. So to calculate that on your calculator, just go second, calculate, which is again trace, and then we want intersect, number 5. So we can, and then when you do intersect, look at the bottom, it says first curve, just hit enter. It'll switch over to your other curve, hit enter again, and then you don't have to do a good guess, so just hit enter again. It gives you the answer, and notice it's the exact same answer we found by hand, 7.477 in days. Okay, so this is getting really long, but I want us to solve the second part, the doubling time, before we go. So I'm going to move this over a little because I am really running out of space on this problem. You probably are too. So it says, what is the doubling time for this population? I love those questions. I think that's almost the most fun part. It's so sciencey. All right, so for the doubling time, what letter is that? F. Wonderful. Okay. There. We are saying if our equation was amount at time t is equal to 100 e to the 0.045 t, okay, then if we want to know the doubling time, that means we want to know when the A of t is equal to 200, right? Because it was 100, so we need to double it. All right, to solve this, we solve the exact same way we did in part E. Okay, divide that by 100, so that's 2 equals e to the 0.045 t. Change to natural log, so natural log of 2 equals 0.045 t. Divide both sides by 0.045. So t is about, and then we have to use our calculator to tell us. You want to hit second quit out of the graph. Okay. And then natural log of 2, end parenthesis, divided by 0.045, enter. 15.403 days. Okay. So the bacteria will totally double in 15 days or so.